Okay, so electrolysis, we've heard this term before. This is an everyday word in our vocabulary. Electrolysis takes place in an electrolytic cell, and it means to break apart. It's not to be confused with an electrochemical cell. They're not interchangeable. Electrochemical cell simply means you're either going to be looking at a voltaic or an electrolytic cell because you're having a change from chemical energy to electrical energy or electrical energy to chemical energy. That's all an electrochemical cell means. A change from electricity, electro, to chemical chemistry. Okay? So, electrolysis, or electrolytic cell and electrochemical cell are not interchangeable. So it says, consider the electrolysis of Ki. Identify and write out the half reactions, write out the redox reaction, and label a diagram. So, first step that you have to do is you have to list all of the species present in that reaction. Okay, so Ki, what are the species that we're going to have?
Potassium.
So we're going to have potassium. What else are we going to have?
Iodine.
And one more?
Water.
Water. Okay, the reason we're saying water, it's aqueous. So, next thing that we have to do is, this is electrolysis. So, which one is going to be the strongest reducing agent? Which one's going to be the strongest oxidizing agent? Because it's electrolysis, your reducing agent has to be greater than your oxidizing agent. Okay? So it's non-spontaneous. So when we know that it's non-spontaneous, which one becomes our quote-unquote strongest reducing agent then?
Iodine.
Oh, I spelled strongest wrong. Okay, so then what becomes our strongest oxidizing agent? Okay, it's an oxidizing agent. And this also becomes an oxidizing agent. And when we look,
Water's higher than potassium.
water's higher than potassium.
Potassium's
Yeah.
actually pretty weak as an oxidizing agent.
And water is going to be well, as an oxidizing agent, I find it at plus 0.4. I would go with water because K is near the very bottom. So it is an oxidizing agent, but this is the strongest. Okay? So, reducing agent we find in oxidation. So, whoops. And our oxidizing agent. those are the two half reactions that we're going to go with.
Where on the data sheet is the? What you did
Let me
there?
look.
What's the bottom? No, the neighbors.
Right there, negative 0.83 Mac.
Okay. So why would you use that one, not the?
Not the one at 0.4,
Yeah.
because it includes oxygen. This is just water as your oxidizing agent. Right? It's the sole
Okay, yeah.
species on that side of the equation.
Okay.
Okay? Okay. And now we're going to look at the diagram. So we're going to do this just a little bit differently. We're going to do our cathode, or our electrode. Let's use that term instead. Okay, so we have our electrodes. We have our solution. We know that it has to be joined by a battery. And we know that this is an electrolytic cell. So at the anode, we're going to find the iodine reaction. And at the cathode, we're going to find the water reaction. Okay? So what we're going to look at this particular case, because it's aqueous and there's no, in the description of the sentence it says, consider the electrolysis of Ki. So we're going to pick an inert electrode. Okay?
And just because it's stated that Ki is aqueous, we know it's like the electrolyte solution.
Yeah. Yep. Exactly. So we have K ions in here, and we have iodine ions in there, and obviously we have water in there. So, cathode, anode, and we have a battery. So we know in an electrolytic cell that our electrons are going to flow this way. From the anode to the cathode, that part didn't change, right? So what we see here, we're going to see on this particular one, I'm going to do it in red, we're going to see bubbles. We're going to see H2 bubbles forming on there from the water. And down here, we're going to see the I2 solid is going to build up. So K is going to flow this way, and I is going to flow this way.
So what would those potassium ions do? Are they going to precipitate out on the cathode, or are they spectators at this point?
They stay,
In solution and bind with the hydroxide, and you get like
probably get KOH.
the potassium hydroxide.
Yeah, because your hydrogen is, you're getting hydrogen bubbles.
Yeah.
So now you, instead of having water, you have an H molecule and an OH molecule.
Yeah.
So every 2 water molecules, you're going to get 1 hydrogen gas molecule form. but now you have two OH molecules floating around in solution, so your K is going to attach onto the OH, but because it's got very high solubility, the OH and the K end up becoming spectator ions. So they form and break apart, form and break apart.
So that solution would start to become more basic then?
Yeah.
Okay.
Okay? Now, just like with the English language, there's always an exception to the rule. That's what you wanted to hear. We have what's called the chloride anomaly. Okay? Chloride anomaly occurs in aqueous solutions, so this is really key, this here, aqueous solutions, in which chloride ions are present. So even though we have water being the stronger reducing agent, the half reaction with chloride actually takes place. So this one here, oops, it's not plus. Okay, so this is going to be your oxidation half reaction. Oxidation occurs at which anode?
The anode.
Anode.
Oh.
Okay. So let's look at an example of that. Consider the electrolysis of sodium chloride. Identify and write out the half reactions that occur at the anode and cathode. Write out the redox reaction and label the diagram. So, A, list all species. So what are we looking at? We're going to have sodium ions. We're going to have
Chlorine ions.
chloride ions and
Water.
water. Okay? Because it's in an aqueous solution. So when we look at it, we know that it's electrolysis. So the reducing agent has to be greater than the oxidizing agent. So when we look, what do we find works out for that? When you look on your chart.
Chlorine being the reducing agent. And then sodium would be an oxidizing agent.
And water would be your oxidizing agent as well. So this turns out to be our, when we look at it, this is our strongest reducing agent. However, this is our chloride anomaly. So this becomes our new strongest reducing agent. Okay?
So water is a reducing agent or an oxidizing agent?
It's an oxidizing agent, but when you look at it,
Chlorine's way up at the top.
chlorine is at plus 1.36.
Correct.
So it is the strong, we're looking at that, and then it's sodium. So sodium we find, sodium ion we find at negative 2.71, right?
Yeah.
And chloride ion we find at plus 1.36. But don't forget that reducing agents start from the bottom and work up to the top. So that water is before that. Right? Water on the,
And chlorine is still a reducing agent, though, right? Or chloride
yes.
ions,
Yeah.
because we have the Cl minus.
Hang on. So it's this here is the oxidizing agent, and this is the oxidizing agent. We find these actual species on the left-hand side, and we find that on the right-hand side. But when we come across this water, we
So would you go where water is found as a reducing agent at positive 1.23,
Yep.
making it stronger than chlorine?
Yeah. So we find this at, thank you, I was having a hard time finding it. But we find this one at positive 1.22, right? 1.36, sorry. So we come across the water on the right-hand side before we come across chloride. So in theory, water is the higher or the stronger reducing agent because we start strong and we go up to weak. But because we have this anomaly for the chloride ions, this one actually becomes our strongest reducing agent. Okay? So it takes a long time. I must have looked at this 4 or 5 times and still didn't see water right before chlorine. Okay, so make sure that you're going through it line by line, looking for the species itself. Water is on the right-hand side, water is at 1.23. Okay? Make sense? There are little things that you have to look for, but will trip you up in major ways. So it says, write out the half reactions. So at oxidation, we have two electrons. At reduction, we have 2 H2O gives us, oops, gives us hydrogen as a gas and hydroxide. Okay, so the overall reaction is going to be what anode do we find oxidation at? What electrode do we
Anode?
find? And so we find reduction at the cathode. So when we go to draw our picture, we know that it's electrolytic. Okay, so we have to have a battery in there. We know that it's NaCl, aqueous. So our electrodes are going to be inert. Alright. So let's make our electrodes carbon. What else could we make them?
Platinum.
Platinum. Could also be platinum. Okay. So, if we have, we're going to call this side the anode side, and we're going to call this side the cathode side. Electron flow.
Into the cathode.
Perfect. But what reaction do we have happening at the anode?
Oxidation.
Oxidation. So at the anode side, we're going to see hydrogen gas, hydrogen bubbles. No, not hydrogen bubbles. At the anode, we're going to see chlorine. gas bubbles. Okay? On the cathode, we're going to see hydrogen bubbles. And the sodium ions are going to flow which way?
Towards the cathode.
Towards the cathode. And chloride ions are going to flow in towards the anode. Anything else we need to put on our label, on our diagram?
Would you state that there's free hydroxide floating around now?
You could. We can put them over here. You'll end up with sodium hydroxide.
Yeah.
But it's soluble, so you won't see it break out into solutions. Okay. Let's quickly look at let's quickly go towards the helpful hints, which is after your practice problems. So helpful hints to determine anode and cathode. Okay. I don't know what study methods you have, but this is one of the things that you need to straighten out in your brain. So if you need to make cue cards or you need to make yourself a poster chart or whatever you need to do, you need to sort out voltaic versus electrolytic. So voltaic. What's something that we know about voltaic?
Spontaneous.
Spontaneous. And spontaneous means what? Oxidizing agent is greater than the reducing agent. Okay? So the cathode, which reaction happens at the cathode?
Or reduction.
Reduction. And so what we also know about that is that it's a more positive reduction potential. Okay. The anode. What reaction happens at the anode?
Oxidation.
Oxidation. Which means that you're going to have a more negative electrolytic cell. Whoops. What do we know about electrolytic cells?
Non-spontaneous.
Non-spontaneous. Which means what?
Reducing agents more than the oxidation.
Reducing agent is greater than your oxidizing agent. So, again, we have a cathode. What happens at the cathode?
Reduction.
Reduction. Doesn't change. However, we're going to see a more negative reduction potential here. So if they gave you a bunch of numbers, you should be able, in theory, to look at your table and see if what the reduction potential is. That's what's on the side, standard reduction potentials. And if you have a more negative number, but your reaction is actually happening, then you know it's electrolytic. Anode. What happens at the anode?
Oxidation.
Oxidation. It doesn't change. However, you'll have a more positive reduction potential. Two things to note or here, generates a voltage. This one here requires a battery. So this is chemical to electrical energy. Remember, energy can't be created or destroyed, it can only be transferred or transformed. So this one is going to become electrical energy to force that reaction to happen. Okay? Those are your biggest takeaways.